Okay, students, this is section 4.5, modeling with exponential and logarithmic functions. In this section, I will be working with problems that will span PowerPoint slides 9 through 12. So here is the first problem. So here's the problem. They say strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones. The half-life of strontium-90 is 28 years, meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. The problem asks, or I should say the first part of the problem asks, to find the exponential decay model for strontium-90. So we want to find the exponential decay model, which means we have to find an exponential function that models this specific problem. And then part B asks the following. Suppose that a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take for strontium-90 to decay to a level of 10 grams? So in the second part, we want to know how long do we have to wait? How long do we have to look at the clock for 60 grams of strontium-90 to decay to a level of 10 grams. So the first part of the problem, we'll have to come up with a decay model, or the exponential function that models the problem. And so the basic formula is this. It is A is equal to A sub 0 e to the kt. So in this particular problem, A represents the amount of strontium-90 at any time t, and A sub 0 represents the amount of strontium-90 in the body at time t equals 0. So when we turn on the clock, what is the initial amount of strontium-90 in the body? That's what A sub 0 is. So I like to organize my information in a table, so I know that at time t equals 0, there is 60 grams of strontium-90. So that means that A sub 0 is equal to 60. So since I know A sub 0 is equal to 60, and since I know what my basic formula is, I can put those two ideas together, and I come up with the formula A is equal to 60 times e to the kt. So I almost have my decay model determined. The only thing I don't know is the value of k. So that's what I need to figure out. I need to find the value of k so that I will be able to find my decay model. So here, this is what we need to do to figure out the value of k. We have to take into account the half-life of strontium-90. So we know the half-life of strontium-90 is 28 years. So what this means is that if we had an initial amount of 60 grams of strontium-90, then we would have to wait 28 years for that 60 grams to decay to 30 grams. So what we're going to do is to use the information from the half-life to help us figure out the value of k. So that means that if the half-life is 28 years, we know that the value of A must be 30 when t is equal to 28, because we had an initial amount of 60. When we wait 28 years, we know that amount of 60 will decay to 30. So that means that we know that the value of A is equal to 30 grams. So what we're going to do is we're going to substitute A equals 30 into our formula. A is equal to 60 e to the kt. Here it is here down here as well. And then we'll solve for k. Notice that this is an exponential equation, so we can always recognize an exponential equation by the location of the variable. Notice that the variable is up there where the exponents are. So what we're going to do is we're going to isolate this exponential expression. So you see that 60 is multiplied to that expression. So what we're going to need to do is to divide both sides of the equation by 60. So that's what I do here, and so I end up with this fraction, 30 divided by 60 is equal to e raised to the 28k. I decided to express my fraction as a decimal, so here I have that here. So it's now 0.5 is equal to e raised to the 28k power. And now what I'm going to do is I'm going to introduce my natural log function next. So I'm going to use the fact that if two numbers are equal, if you substitute those numbers into the same natural log function, the results are going to be equal. So here, that leads to this equation. So now I have the natural log of 0.5 is equal to the natural log of e raised to the 28k power. Now I can take advantage of the property that says if you have an exponential function substituted into a log function with the same base, these two functions in some sense cancel each other out, and we get the exponent that you see here. So here, simplifying, my equation becomes the natural log of 0.5 is equal to 28k. So now this is a simple linear equation because the equation is in the form number times letter is equal to number. So if I want to know the value of the letter, I just divide both sides of the equation by 28. So I'm going to divide both sides of the equation by 28, and so we have this new fraction here. And then what we need to do is to substitute that into our calculator, and we get that value. So we get a negative value. So this is consistent with having exponential decay. So if we have exponential decay, then that means that the value of k will be negative. So now we take this value of k, and it's a pretty long, it has a lot of digits. So what I decided to do was to approximate k to 4 significant digits. So here k is approximately equal to negative 0.2476. And so now that I know the value of k, I have my decay model or decay formula. So here, the amount of strontium-90 is given by this formula. So A is approximately equal to 60 times e raised to the negative 0.02476 t. So now I'm ready to answer the second part of this question. That is, how long does it take strontium-90 to decay to 10 grams? So here we're assuming that we started with an initial amount of 60 grams, and we want to know how long do we have to look at the clock for the amount of strontium to decay to 10 grams. So we go back to our formula that we derived. So our formula is A is equal to 60 times e to the negative 0.02476 t power. And what we need to do is to substitute A with the value of 10. So if I do that, I end up with this equation that you see here. Again, now you notice that yet again I have an exponential equation. So I'm going to isolate this exponential expression. Notice 60 is multiplied to that expression. So I'm going to divide both sides of that equation by 60 to isolate the exponential expression that I have here. So after dividing both sides by 60, I end up with this equation here. So this is 10 divided by 60 is equal to that exponential expression. So I'm going to apply the natural log to both sides. Also notice that, of course, 10 and 60, they're both divisible by 10, so I'm going to reduce that fraction. And so putting those two ideas together, we end up with this equation here that you see. So this is the natural log of 1/6 is equal to the natural log of e raised to the negative 0.02476 t power. Again, we can use our inverse properties for exponential and log functions. So if we have an exponential function, substitute it into a log function with the same base. So here the exponential expression has base e, and of course the natural log function by definition has base e. So those two functions essentially cancel each other out, and we end up with this expression here. Natural log of 1/6 is equal to negative 0.02476 t. So given that we have that formula, we can solve for t by dividing by this decimal number here. So if we divide both sides by negative 0.02476, we end up with this fraction. And so what we need to do is to put that fraction, evaluate that fraction using our calculator. When we do that, we end up with t is approximately 72.37. And so now that we know that t is equal to 72.37 years, we can answer part B of this question. That is, it takes approximately 72 years. So it takes approximately a lifetime for strontium-90 to decay to 10 grams.